Good morning to one all present here. I am Tanya Thangashan. Today I am going to present about the common emitter amplifier. These are the contents we are going to discuss today. Introduction. There are three amplifier configurations. They are common emitter, common base and common collector. The common emitter is the one we are going to discuss today. The common emitter configuration has the emitter as the common terminal or ground to an AC signal. CE amplifiers exhibit high voltage gain and high current gain. In this slide, we can see the figure of common emitter amplifier. The common emitter amplifier with voltage divider bias and coupling capacitor C1 and C3 on the input and output and a bias capacitor C2 from the emitter to the ground. The input signal V input is capacitively coupled to the base terminal. The output signal V out is capacitively coupled from collector to the load. The amplified output is 180-degree out of phase with input. Because the AC signal is applied to the base terminal, the input and taken from the collector terminal as output. The emitter is common to both input and output signals. Phase inversion. The output signal is 180-degree out of phase with the input signal. As the input signal voltage changes, it causes the AC base current to change, resulting in a change in the collector current from Q point value. If the base current increases, the collector current increases above its Q point value, causing an increase in the voltage drop across the RC. This increase in the voltage across RC means that the voltage at the collector decreases from its Q point. So any change in input signal voltage results in an opposite change in the collector signal voltage, which is a phase inversion. DC analysis. The DC bias values must first be determined. To do this, a DC equivalent circuit is developed by removing the coupling and bypass capacitors because they appear open as far as the DC bias is concerned. This also removes the load resistor and signal source. AC analysis. To analyze the AC signal operation of an amplifier, an AC equivalent circuit is developed as follows. The capacitors C1, C2 and C3 are replaced by effective shorts because their values are selected so that XC is negligible at the signal frequency and can be considered to be 0 ohm. The DC source is replaced by ground. A DC voltage source has an internal resistance of near 0 ohm because it holds a constant voltage independent of the load. No AC voltage can be developed across it, so it appears as an AC short. This is why a DC source is called an AC ground. In an AC analysis, the AC ground and the actual ground are treated as same point electrically. A common emitter amplifier because the bypass capacitor C2 keeps the emitter at an AC ground. Ground is the common point in the circuit. Signal AC voltage at the base. The AC source has a non-zero internal resistance. Then three factors must be taken into account in determining the actual signal voltage at the base. These are the source resistance, the base resistance and the AC input resistance at the base of the transistor. This is illustrated in the figure given below. You can check the figure given below. A high value of input resistance is desirable so that the amplifier will not excessively load the signal source. This is opposite to the requirement of stable Q point, which requires small resistors. The conflicting requirement for high input resistance and stable biasing is but one of many trades-off that must be considered when choosing components for the circuit. The total input resistance is expressed by the formula R in total equal to R1 parallel to R2 parallel to R in base. Input resistance at the base. The input resistance at the base is that to develop an expression for the AC input resistance looking in at the base, use the simplified R parameter model of the transistor. The transistor model connected to the external collector resistor. The input resistor looking in the base is R in base equal to V input by I input equal to VB by IB. The final equation is R in base equal to beta AC RE. Output resistance. The output resistance of the common emitter amplifier is the resistance looking in at the collector and is approximately equal to the common collector resistance. R output is equal to RC. Voltage gain. The AC voltage gain expression for the common emitter amplifier is developed using the model circuit. The gain is the ratio of AC voltage at the collector VC to AC input voltage. The equation is AV equal to V output by V input. It can also be written as VC by VB. The final equation is AV equal to RC by RE. Attenuation. The attenuation is the reduction in signal voltage as it passes through a circuit and corresponds to gain of less than 1. For example, if the signal amplitude is reduced by half, the attenuation is 2, which can be expressed as a gain of 0.5 because gain is reciprocal of attenuation. Suppose a source produces 10 mV input signal and the source resistance combined with the load resistance results in a 2 mV output signal. In this case, attenuation is 10 by 2 equal to 5. That is, the input signal is reduced by a factor of 5. This can be expressed in terms of gain as 1 by 5 equal to 0.2. Attenuation equal to Rs plus Rn total by Rn total. This diagram is base circuit attenuation and overall voltage gain. Effect of emitter bypass capacitor on voltage gain. The emitter bypass capacitor provides an effective shock to the AC signal around the emitter resistance, thus keeping the emitter at AC ground, as you have seen. With the bypass capacitor, the gain of a given amplifier is maximum and equal to RC by RE. The value of the bypass capacitor must be large enough so that its reactance over the frequency range of amplifier is very small compared to RE. A good rule of thumb is the capacitive reactance of the bypass capacitor should be at least 10 times smaller than RE at minimum frequency of the amplifier must operate. Voltage gain without the bypass capacitor. Without the bypass capacitor, the emitter is no longer at an AC ground. Instead, RE is seen by the AC signal between the emitter and the ground and effectively adds to RE in the voltage gain formula. AV equal to RC by RE plus RE. The effect of RE is to decrease the AC voltage gain. Effect of a load on the voltage gain. A load is the amount of current drawn from the output of an amplifier or other circuit through a load resistance. RL is connected to the output through the coupling capacitor C. The collector resistance at the signal frequency is effectively RC in parallel with RL. AV equal to RC by RE. Stability of voltage gain. Stability is a measure of how well an amplifier maintains its design value over changes in temperature or for a transistor with a different beta, although by passing RE does produce the maximum voltage gain, there is stability problem because an AC voltage gain is dependent on RE since AV equal to RC by RE. RE depends on IE and on temperature. This causes the gain to be unstable over changes in temperature because when RE increases, the gain decreases and vice versa. AV equal to RC by RE. Swamping RE to stabilize the voltage gain. Swamping is a method used to minimize the effect of RE without reducing the voltage gain to its minimum value. This method swamps out the effect of RE on the voltage gain. Swamping is in effect a compromise between having a bypass capacitor across RE and having no bypass capacitor at all. In a swamped amplifier, R is partially bypassed so that reasonable gain can be achieved. AV equal to RC by RE1. The effect of swamping of the amplifier input resistance. The AC input resistance looking in at the base of a common emitter amplifier with R is completely bypassed in R in equal to beta AC RE. When the emitter resistance is partially bypassed, the portion of the resistance that is unbypassed is seen by the AC signal and results in the increase in the AC resistance by appearing in series with RE. The formula is R in base equal to beta AC RE plus RE1. Current gain. The current gain from the base to collector is the overall current gain of the common emitter amplifier is IC by IB or beta AC. The formula is AI equal to IC by IS. IS is the total signal input current produced by the source. IS is also having a formula that is IS equal to VS by RS plus RN total. The power gain. The overall power gain is the product of the overall voltage gain and overall current gain. That is AP equal to AV into AI, where AV equal to VC by VS. The reference is from Electronic Devices of the author Thomas L. Floyd. Thank you.